sustainability goals through energy savings on dust collectors. Me being the Vice President of Sales here within Adams, and Nate Valentin, our Vice President of Innovation. So a little bit about Adams to start us out. We're a value-added distributor established here in 1960 here in Tampa, Florida, on the third generation of the family running this business, focused on supporting customers and achieving their goals around reliability and automation. A little bit about myself. Background is electrical engineering. I've been in the industry for 13 years, starting with Adams as a technical sales rep based in Jacksonville back in 2011. And I've been specifically working with dust collection for the last 9 years. Sometimes I even get my hands dirty, as you see here. So my goal for this webinar is to allow us to discuss dust collection, its operation and typical operation inefficiencies from what we've seen, the energy demand of these systems, and where and why we've found success with these systems. So the conversation around sustainability is kind of where I wanted to start. So sustainability is a big initiative from a lot of our customers and a lot of industries we see. And the main reason I wanted to talk about this here is because one of the key pillars of sustainability is its environmental and economic impact. And that impact is driven based on energy demand. And so how can we work with customers to reduce that energy and to provide them a lot more efficiency around their energy consumption? As I mentioned, big push from a lot of our customers. So I wanted to highlight some of the customers that we work with, big names that you might know across vast different industries, but each of them focusing on initiatives to reduce energy consumption, to be more energy efficient, and to find ways to use technology that allow them to improve those energy consumptions. Beyond those industries that you saw, I wanted to highlight a little bit of the other industries that we might deal with. And as you can see, it's pretty vast in the industries that we work with. We see dust collectors throughout many manufacturing processes, many manufacturing plants, and there's not many industries that aren't utilizing them to some extent. So why dust collection? So typically we're seeing these in 3 different categories. This is around controlling emissions as driven by the EPA. This is around indoor air quality, as you might see driven from OSHA's standpoint, or in the manufacturing process of the product that that customer might be manufacturing. So think about a cement plant and a raw mill being used in that process of the manufacturing. There's 4 different types of dust collectors that we typically see in the industry. The main one that we focus on, and the main one that I'll be discussing today, is pulse jet baghouses. So I wanted to start with a little bit of the operations on how these are used. So what you'll see is this is coming in with vacuum pulling dirty air into the system. That system has baffles that allows the air to be spread evenly through the filters that are in that collector. The filters are driven to catch the dirty contaminants, and then clean air is driven out of the system. Here's a few examples of what these might look like in a manufacturing space. So I wanted to dive in a little bit deeper, specifically around the cleaning system of these pulse jet collectors. So typically what you're seeing in these systems is you have a header where the volume of air is being held. That header is leading to a diaphragm valve and leading into a blowpipe. That diaphragm valve is triggered by a remote bleed solenoid valve. Upon the air flowing through the blowpipe, you're going into a venturi that is then cleaning the filter. And to show a little bit more about how that process works, this is a non-fired filter, and then when the pulse valve is engaged, you see that the air comes through the blowpipe through the venturi and creates a wave type effect that knocks the contaminants off of the filters. The technology used, and that has been used for many years in this operation of these pulse check collectors, is a diaphragm valve technology. Unfortunately, with that technology, there's inefficiencies that degrade over time and that cause the operation of these systems to not be as effective as they should be. When working with customers, we see that typically to overcome these deficiencies, what they do is follow 4 reactions of these systems. So they'll typically start by increasing the pressure operating on these systems, feeling that the higher pressure will allow us to be able to clean the filters better. When that doesn't necessarily solve the problems, they'll then follow up by increasing the pulse frequency, that is how often these valves are fired, to get them to pulse the filters more frequently to try to clean the dust off of those filters. Next step they'll do is they'll increase the on time. The on time is how long that solenoid is engaged and how long that valve is held open. Following these 3 processes, if they're still not able to control the differential pressure on the systems and get the systems to operate as effectively as they should, they'll end up replacing the filters. All of these end up creating a significant amount of operating cost for these systems, all revolved around the valve technology that's just not being used properly to allow these systems to operate as well as they should. So how are we different? So the valve technology that we use is a spool valve technology versus a diaphragm technology. That spool valve is also operated by a 4-way pilot, allowing us to shift the spool back and forth via air. So with these, we're able to see multiple advantages in the operation of the systems, but where we're focusing today is around energy savings and filter bag life. How we're able to achieve this is really around pulse efficiency. So I wanted to use this kind of scope here to give us an example of how we're operating these systems much better, just simply by changing the valve technology that's on there. As you can see in this scope, we're engaged from an electrical standpoint on the same amount of time frame. We're operating with the same amount of system pressure, but what we're able to do is achieve a higher impact force because of our pressure drop over our valve being significantly less than the existing diaphragm technology. And with our spool design utilizing air and a heavy spring to close it, we're able to close that valve in a much sharper time frame, creating a much sharper ripple effect and a much sharper cleaning pulse on those filters. And what that looks like in operation, you can see here in this video. And I'll play this video one more time, but as you can see, there's a standard diaphragm valve operating this row of filters here, and the second row of filters is being operated by a MAC pulse valve. So you see significantly more dust is being pulsed off of that filter, dropped down to the bottom of the hopper to be collected through their system, and allowing the differential pressure of those filters to be significantly less, so it has to fire off less often. Here's another visual representation that I just felt was pretty impactful to show. So this is a customer's clogged filters on their dust collector. The customer then installing new filters and doing nothing but putting a MAC pulse valve on one of the channels and leaving the diaphragm valves on the separate channels. So after 3 weeks, you can see that just the one channel with the MAC pulse valve is significantly cleaner than those channels where it's operating the Goyen valve or the diaphragm valve still. One thing to note about filter life is these filters have an impact life rating specifying how often they're able to be pulsed. We're typically seeing that this could be anywhere from 100,000 cycles to 150,000 cycles. So if we're able to clean the filter per pulse more efficiently, we can then theoretically extend the filter life because we don't have to pulse them as frequently, which results in us being able to accomplish some sustainability goals by reducing the number of filters heading to the landfills. So from filter life, I want to talk about energy. As I highlighted, I really wanted to talk about filter life savings and the energy impact of these systems. So the first place I wanted to start was a pretty significant case study that we worked with one of our customers here, that were actually awarded the best of the betters for the Better Building Bureau in the Department of Energy. So in this presentation and in this application that we worked with them on, they were able to identify compressed air as one of the least efficient utilities in industrial plants. And then they were able to see that their dust collectors were the main consumers of these of this compressed air. And that's what we see in multiple industries. So what they wanted to do is they wanted to drive an initiative on how they could reduce the air used in those dust collectors to improve the performance of them and improve the efficiency and reduce the environmental impact of this. Working with our team and the customer and implementing the MAC pulse valve technology and allowing them to better optimize their system, this plant, as an example, was able to reduce the operating pressure from 100 psi to 85 psi, allowing them to shut down a compressor. Rolling this out across multiple collectors, they were able to reduce air consumption around 20% throughout the facility, shutting down additional collectors and providing a financial impact of $68,000 savings. This is something that drove them to make an initiative to upgrade their pulse valves throughout all of their plants globally to the MAC spool valve technology. And I just wanted to highlight another article around this same implementation from compressed air best practices as well. Sticking with the philosophy of third-party comparisons, just to be able to show some data. I'm very much a data person, so want to be able to provide this as much as possible. So this Compressor Energy Services is a company out of the Northeast that was able to work with one of our customers, evaluating the flow consumed on a single dust collector that operated with 30 valves. In their evaluation, they were able to see that this collector was using an average airflow of 42 CFM, equating in about $7,000 of operating costs just dedicated to the air consumed in that collector. Doing nothing but just changing the valves on that collector, they were able to reduce the air consumption on that collector by about 55%. And then following up on that, changing the operating settings due to the valve upgrade and what it was enabling, we were able to see them drop the air consumption down another 8 CFM to 11 CFM. This allowed the customer to reduce the flow in that system around 74% and reduce that system operating costs from $7,000 all the way down below $1,800 and get $5,200 out of the operating cost just of the air of that system. One thing to mention here that was done in this study too is the failure mode of these existing designs are designed to fail open. It's a remote bleed system that when the valve fails, air is constantly flowing into that blowpipe that I showed. What that means in your system as far as the air consumed and the cost consumed is shown very well here in this chart. So this chart shows installing a failed valve and the air consumption that's driven just by that valve. So just in the design of the valves failing open, that can significantly draw air demand, energy demand, potentially even pulling down compressors from what we've seen with some of our customers. Whereas the spool valve technology is designed to fail closed. So if the valve ever were to fail, it's going to fail in a closed state, not driving air through that header, through that valve, and allowing the other valves and the other channels to operate as effectively as they need to. So I wanted to allow us to highlight on our process. So our process is to visit with customers to survey existing collectors. What we work with these customers is to go identify the valves utilized in these systems, identify the existing settings and the operational data, gathering as much information as we can about how that system currently is operating, what the differential pressure settings are, what the on time is, what the off time is, how long the filters are lasting, and gathering all of that data. From there, we're taking that data back, putting together a proposal for our customers to allow us to present a proposal for what the upgrade would look like and the anticipated cost savings and total operating cost of these systems after the implementation of the pulse valve, MAC valve technology. What this allows us to do is show the customers what their ROI would look like based on this investment. Following the order of these systems, our team's working with customers on training them how to properly install these valves, because it is important to make sure that you're putting these in properly, that you're utilizing the expertise that we have and what we have learned through this process on how to make sure these valves are operating as efficiently as possible. We're then going to make sure that the system settings are as optimal as possible, dialing back down that on time so you're not firing for a longer period of time than you need to, and also allowing us to potentially go to a pulse on demand versus a pulse on time setting to allow you to truly only fire when that system is needed versus on a specified time period that someone decided to set it to. Following that process discussion, I just wanted to allow us to talk through some different examples and give some examples of where we've been able to implement this with success to show customers how they can see the impact in their systems through examples that we've done before. So here's an example of a pharmaceutical manufacturer that we worked with, where we were able to show them significant savings around both energy and around filter life improvements to give them an ROI of about 6 months to a half year, which is a pretty standard time frame that we're seeing with customers. This one's pretty impactful. This is a customer in steel mill, and we didn't even look at filter life in here. We wanted to specifically just look at energy savings. And what they saw in our evaluation and what we saw in our evaluation is the amount of cost that was being driven from the operation of these existing diaphragm valves. That these valves were taking significant amount of time to close, thinking about back to that pulse efficiency. As you can see here, 30 to 45 seconds for these diaphragms to fully close. And you think about that as far as how long these systems are open, these valves are open, that is just dead, wasted air. That's not cleaning the filter, it's just dragging that out. And what we're able to do just by implementing the MAC valves is to allow that closing to be in the milliseconds range as it should be, because you're able to use our valve technology and the air from the four-way pilot to shift this back and forth effectively to provide that sharp pulse, to fire less often, to clean these filters and extend the time in between these filters being pulsed. Another example here was pretty powerful example too. This was a customer in the gypsum industry that implemented our valves on one dust collector that was mirrored from another collector just right in front of it. So this example shows kind of an existing diaphragm valve technology collector and our valve collector here that allowed to show these systems operate exactly the same. The only thing that was different was the valves being changed. And you can see the header pressure, the pipe diameter, the flow coefficient, everything's uniform. And then what it comes down to is kind of the consumption. So how often is it cycling? You see 700 for the existing diaphragms, 250 for the MAC valves. Same amount of pulse valves throughout, 54 on each collector, and then the number of consumption in cubic feet per hour. Operational hours are the same, and the consumption per year. So you look at just the operating cost of these two collectors, one being around 27,000, and then after the upgrade for the MAC valves, the other being under 5,000. So a significant amount of savings with this being just two of the dust collectors in their full plant. And this is really where I want customers to kind of see the impact that this can make. Simply just changing the valve technology and allowing these systems to operate as they should. Here another example in a paper mill where we were able to work with a customer to upgrade these pulse valves on their powerhouse. And this was highlighting energy savings, filter life, and also operational costs in regards to having to change these valves that you would have to get a lift to be able to get to. So there's multiple levels of this improvement, but realistically looking at the two things regarding sustainability, our energy savings and our filter life extension, just those two equate to over $4,000 in savings just for a small collector here that only had 10 valves. Talking through our process, what I wanted to make sure we didn't necessarily negate, and we kind of emphasized and talked through a little bit more, it's really us coming back out and us working with customers to make sure these systems are operating and the settings are how they should. There's a customer that had made an upgrade to the MAC pulse valves, and a couple weeks into its operation, we wanted to come through, make sure the system was operating as it should, the settings were optimal. What we found is that the settings hadn't been adjusted from the previous diaphragm valves. And what that equated to is the valves were being operated at 400 milliseconds on time and being pulsed 9 times per minute. Through optimizing that system, through monitoring the differential pressure, and through changing the on time to what it should be, we brought that on time to 140 milliseconds, and we dropped the pulses per minute to 3. And just those settings on that one 9-valve collector was able to provide the customer $24,000 in annual savings here. So you see there's multiple examples here, and this is just a few that I wanted to show you. But realistically, the amount of cost that you can save from an energy consumption standpoint to achieve those sustainability goals, to reducing energy consumption and to make the energy that you're using operate more efficiently, that's really something that we're able to achieve with customers on a regular basis. So we wanted to make sure that this was known throughout, and that's the reason why we wanted to have this webinar. So that's where I'll finish, kind of a quick run through of that information. Love to have any questions that customers might have, anybody might have on this call. But yeah.
So right now, I don't see any questions just yet. If you have a question, like I said before, raise your hand or you can put it into the chat. just so everybody understands, we will be sending out a recording of this webinar as well. So if there's anyone on your team that wasn't able to make it, please share it with them. If you have any questions, you could always reach out to us. Just give people a few seconds. I'm not seeing any questions, so I guess you did a good job explaining stuff, buddy.
Cool.
All right, well, thank you all for joining. We appreciate your time. You guys have a great day, and you should receive that webinar recording from us in the next couple of days. Thank you.
Cool. Thanks, everybody. Have a great day.